We at General Dynamics Convair are justly proud of our achievements in space. We are also pleased with the progress we have made in the research and development of composite materials for structures and components to be used in space. Without this progress, America's space ventures, such as the Space Shuttle Orbiter, would be seriously hampered. We believe that increased use of composite materials is the key to resolving many of the problems which arise from the use in space of such metals as aluminum. And to back up our belief, we can point to a number of successful projects pertaining to the use of composites which are making special contributions to America's space program. We are leaders in composites for spacecraft, including laser mirrors, an optical bench, shuttle remote manipulating system arm booms, the HACL telescope, the GEMS space telescope, missile adapters, the Nimbus G antenna, technology antennas, deployable antennas, and the Space Shuttle Orbiter mid-fuselage. Not least is our developing capability in the field of automatic fabrication of space structures. Such structures provide ideal applications for composite materials such as graphite fiber fabrics in thermoplastic resin matrix. The characteristics of graphite thermoplastic include low density, up to 40% lower than aluminum, high stiffness, up to 4 times stiffer than aluminum, high strength, can be up to 3 times stronger than aluminum, low thermal expansion, as low as 1/1000th that of aluminum, high fatigue strength, usually 2 times that of aluminum. It can be automatically pre-processed in long continuous strips, including application of a special coating for resistance to radiation in space. In-orbit fabrication operations require little energy, only 29% of the available Space Shuttle Orbiter power. The beam builder itself is light in weight, maximizing the amount of deliverable spacecraft materials and equipment. Beam members can be formed automatically and continuously using a proprietary roll-forming process. Beams are joined by ultrasonic welding heads, requiring no adhesives and leaving no debris in space. Composite materials lend themselves to high-density storage, such as the packaging of 3,000 feet or more of graphite thermoplastic rolls in storage canisters, enough for the construction of large structures in a single shuttle flight. The beam building machine has 3 separate cap-forming units, each designed to produce a continuous cap from a thin roll of pre-consolidated graphite thermoplastic composite material. Strips are fed from the cap material storage canisters through the cap forming and drive section in strokes of 1 bay length. When the cap drive pauses, the cross-member storage and feed clips supply a cross-member to a cross-member positioner, which places it in position for welding. The cord storage spools supply cord to be strung diagonally across the bays by cord pliers, which shuttle from side to side. The cross members are welded to the caps by ultrasonic weld heads, and the weld joints also capture the diagonal cords, which have been positioned by the cord pliers. Beam cutoff shears separate the beam from the machine when the programmed length has been obtained. All steps in the process of beam manufacture are automated, and beams can be built of any length. For instance, lengths of 11 meters and 200 meters are proposed for this early demonstration experiment. At the present, we at General Dynamics Convair are developing the capability of manufacturing composite beams such as this one. It's stronger than aluminum and exceedingly light. This is a prototype beam cap roll forming machine, which is the forerunner of machines to be used in space. The process is fully automated and includes the 3 stages of heating, forming, and cooling. A drive unit moves the strip stock through the machine. First, As the flat strip material enters the machine, it is heated to the plastic state along the 3 bend zones, where the radii are to be formed. This strip heating is performed by electrical resistance heating elements and reflectors mounted in the heating section. Sensors monitor the material temperatures in the heated zones for feedback to temperature controllers, which modulate the heat rate of the heater elements. Next, the material passes through the forming section where it is formed to the correct cross-section by sets of forming rollers. Heaters maintain forming temperatures along the bend zones of the material. The configuration of the forming rollers was designed to allow the material to assume a natural shape throughout the transition from flat to formed state. This prevents undesirable buckling or tensile loads in the plastic bend zones. When the predetermined length of material has moved through the machine, 1 bay length, the drive motor pauses. During this pause, the material is cooled by platens to solidify the graphite thermoplastic in the final formed shape. The inside platens are water-cooled, while the 2 outside platens are cooled by conduction and radiation. The cap material is pulled through the process by a friction drive located aft of the cooling section. 4 drive rollers contact the cap in the side bend zones. The pull forces required to form the material are less than 10 pounds, which requires very little power consumption by the drive motor. The maximum power required for heating and driving a cap-forming machine in space has been calculated to be 470 watts. The cap-forming machine is controlled by this process controller, which provides control for all parameters, including temperature, motor speed, and number of cycles. Once all parameters have been set, the operation cycle is initiated by depressing the start button. The machine automatically stops at the completion of the designated number of cycles. Demonstration of the concept of roll-forming graphite thermoplastic composite strips was one of the 2 major subsystem development issues that had to be resolved before a beam-building machine could become reality. The second major subsystem development program was to prove the capabilities of ultrasonic welding. This highly efficient joining technique uses little energy because only the resin under the weld tip between the pieces to be joined is heated to the melting point, then refused. This process works efficiently in the vacuum of space and is reliable and repeatable. The Space Shuttle Orbiter is now a reality, and in due time will be manufacturing large-scale structures in space for a variety of functions. And we at General Dynamics Convair are helping to advance NASA's space construction development objectives. For we have the manufacturing technology for automatic fabrication of composite structures now.